All right, this will be the last video from chapter 4. This one's on dynamics of circular motion. So in this video, we're going to analyze this carnival ride where you're in the cylinder that's spinning around, and if it spins fast enough, the floor can drop underneath you. And so given the radius of the cylinder and the coefficient of static friction, we want to find out how fast does this thing need to rotate in order to stay in equilibrium without the floor there. So actually, so I just want to sum up what's common to all of these problems. We'll do this example problem, and then I'll quickly talk about the 3 example problems that your book does. So in this section, your book goes over 3 example problems as well. Okay, so in general, circular motion dynamics. In general, you want to so the steps that you want to follow here. First of all, draw a free body diagram. This always helps. Second, you want to choose your coordinate system. So that one direction is radially inward. So one direction is the radial direction. It could be radially outward. Radially inward, though, you could set the acceleration, the radial component of the acceleration as a positive number. So I have a slight preference for radially inward. Choose coordinate system, so one direction is radially inward. So the net force is not going to necessarily be 0. So in these problems, this right here, this thing is not going to be in equilibrium for sure. So they won't cancel for sure. If an object is moving in circular motion, these definitely won't cancel. They won't. Handwriting's getting worse and worse every time I redo this. There we go. Choose coordinate system, so one direction is radially inwards, and then the other 2 directions are probably be another one is going to be tangent to the circle, and another is perpendicular to both of those 2 directions. I guess you might call this the R hat direction for radially inwards, the T hat direction, and then I don't know, the Z direction for the one that's perpendicular to both of those. Just because that's a little more telling than X, Y, and Z, right? X, Y, and Z don't really mean anything, but R hat is definitely radially inwards or radially outwards, and then T is the tangential direction. So the third step, I was thinking about how to draw that example when I talk about the Shankar. That's how bad I am at drawing. I have to practice drawing a stick figure. The third thing, so sum of the forces is mass times acceleration for all of these problems. So what this means is that the sum of the forces in the radial direction, so if this is radially inwards, if that's true, then the sum of the forces in the radial component of all of these forces is going to be MAR, and we know that this has to be V squared over R, the radius of the circle. And then the sum of the tangential components of the force, this could be 0, and it might not be equal to 0. So maybe it's equal to 0, maybe it's not equal to 0. It's equal to 0 if you have uniform circular motion. So in other words, if the speed is constant, then this is definitely going to be equal to 0. But later on, so in all of these examples, we'll have the tangential component equals 0. And we're not considering an object that's increasing its speed as well. But later on in the course, we'll look at objects that are increasing in speed as well, going around in circular motion, in which case the sum of the tangential components doesn't have to equal 0 if speed is changing. All right. And then in general, we're not going to make the z component non-zero, just to keep things relatively simple. But this is the key thing for now. Some of the radial components of the forces have to be equal to mv squared over r, just to maintain the circular motion. So that's the way you're going to analyze all of these problems. These steps are going to be in common for all of these things. Right. Okay, so just keeping those steps in mind, we're in a position where we can actually address this problem. So let's do this Carnival ride one. So the first step will be to draw the free body diagram. So original problem. Let's draw it so that the person is on the right-hand side here. I think I had them in red. So the person's pinned against the right-hand side of this cylinder. And I did that to be particular about what the radial direction is. Well, the first step, the free body diagram step, you don't even have to choose the coordinate system. You're just drawing the forces. So there's definitely the weight downward, mg. There's a normal force from the ground. And I'm going to label this lowercase n, the normal force from the ground, because there's another normal force from the wall. Now, why is there a normal force from the wall? So this is the only force that's going to be in the radial direction. The only other one is going to be friction that'll wind up being vertical. So why is there a force in this horizontal direction? Well, this is the thing that's required to keep the person going around in a circle. You know, if there was no force in the horizontal direction, then this person who's going into the page right now, or into the screen right now, so the velocity of this person is into the page, into screen. So if this person's going into the screen, if there were no forces on this person, or if there was no net force on this person, the person would keep moving into the screen. But the velocity needs to change direction in order to maintain the circular motion. So it needs to sort of curve to the left. Right? Going into the page, it needs to curve to the left to maintain the circular motion. There needs to be a net force that has a direction leftward in order to do that. So this is coming from the wall, right here. We're analyzing the problem. We're drawing a free body diagram in an inertial frame. So we're outside of that cylinder. We're not accelerating in the same way that this person is. And so sum of the forces is equal to mass times acceleration. So remember, Newton's laws are valid in an inertial reference frame. So sum of the forces is mass times acceleration. We can use that. This person actually can't use sum of the forces equals mass times acceleration, right? Because they're not in an inertial frame. They're accelerating. So you're going to hear more about this in talking about reference frames. This person, you know, if you imagine yourself in this Carnival ride, you are feeling a force from the wall inward, but in your reference frame, you're not moving. So you're feeling a force, you're feeling a net force, you're feeling a force radially inward, but no other force in that direction. So you're feeling a force, but you're not moving. And so it seems like sum of the forces is not equal to mass times acceleration. So this is why we're drawing this free body diagram. We're analyzing it outside of the cylinder, just so that we can use that equation. Okay, let's finish up the free body diagram though. Now the point of the problem is that the floor is going to disappear. So this n is going to shrink down to 0. So this lowercase n is going to shrink down to 0. So I just want to point out that if n is less than mg, the other force that's going to make up for it is going to be a static frictional force that's upward. Then Fs, static frictional force, is vertically upwards. So I'm going to draw another force here, F sub s. Okay, so sum of the forces is mass times acceleration will give us two different equations. So so I guess based on what I called it before, so the tangential direction would be in the same direction as the velocity. So this is actually in the z direction, that we would say Fs plus n minus mg. That all needs to be 0. So this person has no acceleration in the vertical direction, right? They're not going to start flying, and we don't want them to crash into the floor. So we're going to say all these equal to 0. And then in the radially inwards direction, there's only one force that has a non-zero radial component, and that's n wall. So n wall is the only force in that direction. This is equal to mv squared over r. And actually, because we're going to solve for, the original problem asked for what is the angular speed. So we're going to write this as n wall is mr omega squared. We're actually going to solve for omega. Okay. So before we continue on that, so I just want to point out, so we want to set this thing equal to 0. So we're going to set n equals 0. So Fs has to be a certain amount. So F star, let's say the static friction, but with a star, is exactly the amount needed so that n could go to 0. So Fs is equal to F star. So what this means, using this equation, so notice how if that normal force goes to 0, if we're going to pull the ground out from under this person and still require that they be at rest, that they not accelerate, then Fs needs to be equal to mg. I guess there's no point in calling it star. I don't need to include that. Okay, so Fs has to be equal to mg because we're going to make that normal force 0. Okay. So now what are we going to do with this? So let's go back to the other equation. So where is n wall going to appear in this? Well, this has to do with static friction. So I just want to point out, so the static frictional force, which has to be equal to mg so that the person doesn't fall, there's a limit to how big that can be. So this frictional force has to satisfy the fact that it's less than the maximum amount it can be. And that maximum amount it can be is mu sub s times the normal force. And the normal force here is not the one from the ground, but the one from the wall. Right? It's the wall that's providing the static frictional force upward. So this is mu sub s times n wall. So I'm going to use this thing in red to say F sub s is mg. That's the value it needs to have. And it needs to be less than or equal to, now, mu sub s times n wall. And n wall, I have right here, is mr omega squared. All right, so canceling out mass on both sides and then solving for omega, we get omega is greater than or equal to g over mu sub s times r square root. So the Carnival ride needs to spin fast enough. Notice this is a bigger than or equal to inequality sign. So there's a minimum angular velocity, angular speed that this Carnival ride needs to go in order to keep this person pinned there and not need the ground. And that's this minimum speed. So in terms of answering the original problem, what's the minimum angular speed? It's going to be this thing right here. This is our answer. Okay. So a lot of these problems in your textbook have a similar flavor. You have to be able to draw the free body diagram and then analyze it in just this way. So some of the forces in the radial direction is equal to mv squared over r, and then in other directions, for uniform circular motion, you can set the sum of the forces equal to 0. Some of those components of the forces equal to 0. So 3 examples in Shankar. Let's go over those. So 1, you have a person, long arms, and they are twirling around. You can see why I practiced drawing this. I still don't know how to draw this. They're twirling around a mass that's going around in a circle here, like this. The circle has radius r. Sorry, it's hard to see. Now a free body diagram of this mass going around in that circle, and this is a horizontal circle. This mass, if you're drawing a free body diagram, only has two forces on it. There's the tension that's in the direction that the rope is pulling on it. So there's tension T, and then there's mg. And those are the only two things acting on this. All right, there's nothing else going on. So the tension is it's doing two things at the same time. So if you look at the two components of tension, and the reason we're decomposing the things into this coordinate system is that the fact that this thing is in a horizontal circle tells us that we should probably choose, so the radial direction will be this one, and then this will be like the z direction. So the radial component, the r component of tension, is going to be equal to mv squared over r, right? That's the thing keeping it moving around in a circle. And then the other component of tension, the z component, has to balance mg. So that's just keeping it balanced against its weight. Okay, so the two equations that we can set up are, so the angle with respect to the vertical is theta. So it looks like this one is theta right here. So they said all this in words. They didn't draw a picture. Oh yeah, they did, right here. They have A and B for their first two examples. So using the radial component, we have t cosine theta is mv squared over r. No, t sine theta. I gotta be careful here. This is, so if this is t, then this is t sine theta, and this is t cosine theta. Right? Adjacent over hypotenuse versus opposite over hypotenuse. Okay, so we have that one, and then for the z components, we have this equation, t cosine theta is equal to mg. So actually, I'm going to write it this way, just to emphasize that the left-hand side here, these are components of forces. And these are m times accelerations, m times components of acceleration. Okay, so these are scalar equations because we're taking we're taking the vector equation f equals ma, and this gives us several different equations. So f equals ma, if you dot the radial component into both of these, you get this one right here. So this is the radial components of this equation. And then this is the z components of this equation. Okay. So your book rearranges, so t sine theta equals something, t cosine theta equals mg. So if you divide t sine theta over t cosine theta, which is tangent theta, you get this divided by, and then t cosine theta is mg. So it looks like you get mv squared over r divided by mg, or tangent theta is, the m's cancel out, and you get v squared over rg. Okay, so given in the problem statement is, probably given in the problem statement you're told what the angle is, in which case you could solve for the speed, or if you're told the speed, you could solve for the angle. Okay, and then once you have this relationship, you can plug back into either one to solve for the tension. So your book does that, plugs this back in, solves for the tension, and gets this. T equals mg square root of all that. So you can see the faster you spin this thing, the bigger V gets, the bigger the tension in the rope. And this should make sense from experience. You know, the faster you spin something around in a circle like this, the more you have to pull in on it, right? The bigger that angle gets. So the bigger V gets, also the bigger the angle. And you can also see that from this equation. The bigger V is, the bigger theta is. Okay, the second problem in your textbook, so the example 2, has to do with a car that's on a ramp. Now, this is supposed to be I'm viewing the car from the back. So the car is going into the page. into the screen. So you're looking at the car on a ramp, and it's going about circular motion like this. So you have to imagine it's not going up or down the ramp, but the ramp is kind of curving all the way around too. This is kind of like, I don't watch NASCAR, but you know, it's a car driving around in a circle. It's like that, but the ground that it's on is not completely horizontal. It's banked. So this is called a banked curve. So normally whenever you see a ramp problem, you're used to defining the coordinate system so that one direction is along the ramp. But if you know the car is moving around in a circle like this, that's actually not the best choice for the coordinate system. So notice how the choice of coordinate system right here, the x and y, are actually not along the ramp. Okay, so for most problems, if you know something is going up or down the ramp, then you want to choose one of the directions to be along the ramp. Not in this case. And the reason for that is that you want one of the directions to be in the radial direction. So this is that. So just how to analyze all of these problems, right? Choose your coordinate system so that one direction is radially inwards. So if we know this car is moving around in the circle, we're going to choose one of the directions to be radially inwards. So this is the r hat direction. The tangential direction is straight into the screen, and then I guess this is the z direction right here. Okay. So your car has 2 or 3 forces acting on it. There's definitely the weight, definitely a normal force, and then maybe there could be friction involved as well. So your book analyzes this without friction. So your car, which is on this ramp, has 2 forces, mg and the normal force. So this should look a lot like the first example, right? The normal force is actually doing double duty here. It's doing 2 things. It's providing the horizontal piece, the horizontal component in the radially inward direction, and then it's also balancing the weight. So the normal force is playing the role that tension did in this problem. Right? The tension's doing 2 things. It's keeping it going around the circle, and it's balancing the weight. Same thing with the normal force here. So as a result, you actually get the same exact answer. So here, this is very similar to example 1. And the answer for how you relate the speed and the angle is tangent theta is v squared over g times r. So you'll notice this is exactly the same as what we wrote down in red. Tangent theta is v squared over rg. I don't know why I flipped them right here. It doesn't really matter. So actually there's no friction needed, but you have to be going for a ramp of a particular angle. So if theta is fixed from the beginning of the problem, there's one particular speed. So if you solve this equation for v, there's one particular speed where the normal force will do everything here. You don't need any frictional force this way or this way. You're not going to slide down the ramp nor up the ramp. If you go slower than this, so imagine the car wasn't going any speed at all and there was no friction. In that case, the car is going to slide down the ramp. Right? There would be nothing. If you had this free body diagram, the way we've been analyzing these problems, there's nothing to counteract the car going this way. If the car goes too fast, though, the car appears to go up the ramp. So really what's going on is that the component of the normal force that's in the radially inwards direction is not big enough. So remember, this force, this component is determined by the weight, so that has to be a particular value, and then because of the angle, there's a particular value, so that sets exactly what this is. So if the car is going too fast, then that's not going to be enough to keep it going in circular motion, and so it kind of flies off. The car flies out of the circle. You know, it's going too fast, so it's not going to drop inward to a lower radius, but it's going to go to a higher radius. So what that means is that it's not really flying up the ramp from a fixed point of view, but like if you're rotating around as the ramp is moving, as the car is going around the circle, if you kind of follow the car is going to go up the ramp. That's what I mean by that. So if you allow for friction, you can actually make this problem more interesting and solve for a minimum and maximum speed that the car could go. So like the minimum speed that the car could go, you could have friction that will help you out in this direction. And then for the maximum speed the car could go, remember if the car goes too fast, it would slide up the ramp, so you need friction to be actually going this way. So if you allow for friction, you can solve for a minimum and maximum speed that the car could go and not slip on this ramp. The last example in your book has to do with this loop-the-loop, the famous loop-the-loop problem. And we talked about this before a little bit in class. Example 3. So this has to do with a car going around a circular loop like this and analyzing the car when it's at the very top right here. So it's actually moving to the left at this point. And I don't want to draw, so maybe I'll see on this diagram they drew the velocity going to the left and then also some forces on top. I try to avoid that with the free body diagram. Maybe with colors it's okay. So the velocity is going to the left at that moment. Now I'm going to switch gears when I talk about the forces. There's only two forces acting on this. There's the weight and then the normal force N. Now the normal force, if the car isn't grabbing onto this track right here, if it's just pressing against it, but there's no like hook right here that prevents it from falling down, then the normal force can only point down. It can't go up at all. Okay, these are the only two forces acting on it though, at this moment. So maybe at another moment, the normal force is pointing in a way that makes this a little bit more complicated. But here, it's just these two vertical forces. And so we have some of the forces in the radial direction. They're all only in the radial direction. So it's mg and normal force. Those are the sum of the forces. And then equals mass times acceleration, mv squared over r. Now what your book does is it solves for the normal force for this problem. So what normal force is required to keep this thing going in circular motion? So that's one way to analyze the problem. Let's think about it that way. So normal force is m times, looks like v squared over r minus g. Okay, so that's just rearranging for the normal force. So this is what's required to keep it going in circular motion. Notice how the faster this thing goes, so v can be however big you want. You know, this car could be going however fast you want. The normal force could be infinitely big, you know, the faster this thing goes. So what this means is that the car, you know, if this car is moving super, super fast, you need an extremely big force in order to accelerate it very, very quickly. If it's going less fast, then you know you have a little bit more time for that force to curve its motion, because you want it curved in a prescribed way. You want it to follow exactly that path. So the faster it's going, the bigger force you need to change its direction more quickly. Okay, so that kind of makes sense. There's a relative minus sign here. So if we're following what we said before, that the normal force has to be positive, you know, if there's no hook to keep it on the track, then this thing has to be bigger than or equal to 0. So the faster this thing goes, the bigger the normal force is. The slower it goes, the less the normal force is. But there's a limit, right? N can be 0, but it can't be any smaller than that if it can't point upward. So this thing's bigger than or equal to 0, which says that v squared over r has to be bigger than or equal to g, or v has to be bigger than or equal to square root of g times r. So g times r is the minimum speed that this car needs to be moving at the very top in order to maintain circular motion without falling down. Right? It could go faster than this, in which case a non-zero normal force is required to keep it going along that circular path. Otherwise, it will pierce through the circle, right? Because it's going too fast to maintain that circular motion. So the normal force is, you know, just whatever it needs to be so that this thing doesn't crash into the loop. But yeah, it has to be going a certain minimum speed. So your book solves for that as well. In our idealized coaster without any of this backup, the speed must obey that to safely make the loop. I don't know why they made it a strict inequality rather than greater than or equal to, but it doesn't really matter so much. And then your book reiterates that the velocity the velocity and the acceleration are perpendicular here for uniform circular motion. Okay.